Hey guys, how are you? My name is Dan Shaftab, and I'm discussing a very beautiful problem with you that I've read lately, and I found the solution, so I thought of discussing it with you. Here, let me first read you the question. What it says here: a projectile is shot from a gun at O. All right, a projectile is shot from a gun from O. All right, at a target object which is at P, which is located at P here. Alright, the target object is released at the same instant the projectile is fired. Alright, they are both released downwards here. Alright, the projectile strikes the falling object, alright, here at Q. Alright, prove that this midair collision will result independent of the muzzle velocity. So we have to prove this. This is a very beautiful question, and I have found the solution, and let's see how is it done. How can we prove that this midair collision will result independent of muzzle velocity? So we have here two things: motion of the object that is falling vertically downwards, and motion of a projectile. All right, let's here see. Let's first analyze the motion of the object that is falling vertically downwards, or you can say it's under free fall. All right, first let us see the motion of the falling object. All right, the object is at P here. It is falling downwards. All right, it's under free fall. The object is under free fall. All right, free fall. Most of you already know that under free fall, the initial velocity of the object is 0. All right, here I'm going to write an arrow on it. All right, and acceleration of the object is negative g. That is acceleration due to gravity, but with a negative sign. That's downwards. It's downwards, so we are taking this acceleration negative. All right, so let's find out. We are taking only y coordinates in consideration, because both the coordinates of x coordinates x1 and x1 are same. When we will find the distance from this point to this point using the distance formula, it will come out y2 minus y1. all right, because x1 and x1 will cancel out. So here, final position minus initial position will be equal to, as you can see, that u is 0. all right, ut, let's first write it down, then we can change it, plus half of at squared. all right, here y2 minus y1 equals, u is 0, so we can write it 0 plus, but negative here, because g is negative, so this quantity will be negative half of gt squared. all right, y2 minus y1 gives us negative of gt squared. all right, now here let us see that, let me call this distance from here to point r. all right, d. From O to R, the distance, let the distance be d. all right, now as you can see from the figure, that this becomes a right angle triangle at R, and here is the theta, so the perpendicular becomes PR, and the base is OR. Now from geometric point of view, we can write in right triangle, in a right angled triangle OPR, that is right angled at R. all right, we can write a tan theta equals to PR perpendicular divided by base OR. Since we have already called OR as D here, so I'm gonna write tan theta equals PR over D. all right, so which leaves me with the solution that PR will be equal to D tan theta. all right, so far so good. Let's have it. But if you can take a look over here, what's the y coordinate here? It's 0. And what's the y coordinate here? It's y1. What will be the distance PR? Since the x coordinate is not changing, the distance will be y1 minus 0, that is y1. So PR will be equal to y1 here, PR. So I'm gonna write y1 instead of PR. All right, y1 will be equal to d tan theta. All right, so let me switch it a little bit over here. Let's see, let me draw a line first here. So you can we can here we have a value of y1 equal to d tan theta. We'll substitute this value in this equation here. All right, so let's do it. y2 we don't know what is y2, but y1 we have found out here, d tan theta. So I'm going to write here d tan theta equals to minus half of gt squared. All right, so far so good. So y2 equals d tan theta with the negative of gt squared. All right, let's call this our equation 1. So far so good. We have analyzed our the fall of our object. Now let's get to the other side of the question, that is this pretty little projectile that we are firing towards the object. All right, let us see here. Let me first divide this thing. We are analyzing the projectile now. So the projectile travels the vertical distance of y2 minus 0. All right, y2 minus 0, and it has an acceleration due to gravity that is negative of g. The initial velocity is divided into two components. All right, let me here show you that. This is the vertical component and this is the horizontal component. You call this u cos theta and u sine theta. All right, u sine theta is the initial velocity that is in the vertical direction, and u cos theta is the initial velocity along the horizontal direction, that's along the x-axis and along the y-axis. All right, here let's get back. So I'm gonna write the equation of here of this here over here, y2 minus 0, because the initial point is the origin, that's why it has 0 along this axis. This will be always be 0 along the x-axis. All right, so I'll simplified it a little bit. The highest point that it is gonna reach that it is going to strike at the object is y2. So y2 minus 0 equals y2. All right, it has an initial velocity that I'll take in account along the y-axis. All right, here uy with an arrow over here, t minus half of gt square. All right, here y2 gives us, y2 will give us uy. I'm gonna write it like this, u sine theta, oh this page is slipping, minus half of gt squared. All right, let me get another paper or here. Let's sorry for the paper break. So here we have, since this you can see here the projectile and the object are striking at this point. All right, at y2, at q, the y coordinates of the both of the object as well as the projectile are equal. So this will mean that this y2 and this y2 are equal. All right, so let me call this equation 2 here. So from we can write it over here from equation 1 and 2, from equation 1 and 2. All right, from equation 1 and 2 we get these left hand sides are equal, so the right hand side must also be equal. D tan theta minus half of gt squared should be equal to u sine theta t minus half of gt squared. All right, so far so good. This quantity and this quantity over here will be cancelled out because they are same. Now we are reaching to the conclusion. Hold your hearts for it. So it's pretty exciting. Sine theta, I'm gonna break tan into these sine theta and cos theta equals u sine theta t. All right, I'm gonna cancel out this sine theta and this sine theta over here, which leaves me with only d cos theta equals ut. All right, these two quantities. All right, let's keep it simple. Now I'm gonna take this t towards here, which will leave me here u will be equal to d over t cos theta. Here d cos theta. All right, now comes the point. Here we can see that the d is the distance between these 2 points, O and R. All right, this is constant because you are firing a projectile from a point that will be constant. You are not changing it. All right, and also the angle is constant, so cos theta will also be constant, and the time of flight of the both of the falling object and the projectile will be same. All right, that is t will also be constant. All right, now hence you can say that this u is constant. What is u? U is the muzzle velocity. So here we have proved that this is constant. So my dear friends, I hope you might have liked it. If you like it, hit a thumbs up for it, and also don't forget to subscribe for more weekly videos. If you have any question, you can write it in the comments, and I'll hope you'll do. Thank you very much.